Hello, good morning and good evening, everyone, depending on where you are at. I'd like to kick off the session with Jeorge from Teradyne on an overview of 5G millimeter wave testing and forward-looking on 6G. Jeorge is currently a wireless product marketing strategist at the Teradyne, Boston, USA. He has held various technical and management positions at Teradyne, LightPoint, TransSwitch, and Rockwell Semiconductors. He holds PhD and BS degree in electrical engineering, MS in telecommunications, and MBA. Jeorge has served on the advisory board of directors of the Global Semiconductor Alliance, TUV Renlane of North America. He is the secretary of IEEE 802.11ay task group. He is also the lead co-author of the book Understanding Fabless IC Technology. Jeorge, the floor is all yours.
Thank you. Hello, everyone. I'm here to talk about from 5G millimeter wave to 6G terahertz. What's next in RF test challenges? Is it really too early to start talking about 6G? We're just barely launching 5G. Well, the answer, as you will see, is no. It's not too early. So let's take a look at where are we today. We're here, 2021. And as you can see, we're barely taking off on 5G. And then the question is, when is 6G coming? So if you look at this particular chart, which shows data traffic in hexabytes per month, you will see that we have a long ride to go in wireless, mobile, fixed wireless access data traffic. So wireless is here to stay for a long, long time. We're just getting started. And as you can see here, this thick pipe in 2026 is just the beginning of the next G, 6G. So clearly, we're going to see a continued decline on 4G and an increase in 5G deployment throughout the world. A modest increase in smartphones, but the message here, we have a long ways to go in wireless communications from 5G to 6G in about 5 to 6 years, primarily driven by video, streaming. As we all know, especially last year, we've been users of this type of communications. So let's take a look. There is a new G every 8 to 10 years. This particular slide shows you the evolution of 3G, 4G, 5G, and 6G over time. And in every case, there is a G every 8 to 10 years. 3G started 10 years after 2G, 4G, 8 also after 3G. 5G was a new radio, right? So it's new challenges, but about 10 years after 4G. So that means that we're only 4 to 5 years away from 6G. And the promise of 6G is additional bandwidth, more spectrum. And if we thought with 5G, this lambda wavelength was becoming very, very small, well, with 6G, it would become even smaller, about 60 times smaller in terms of wavelength than 5G. So this brings a question about test techniques, test methodologies, test insertions. What will they be going from millimeter wave 5G to the case of 6G? So what are the use cases that people are talking about 6G? Here in this table, we compare some attributes between 5G and 6G. And really, if you look at the use cases that we've been talking about for 5G, enhanced mobile broadband, ultra reliability, low latency communications, massive, et cetera, you see that they're similar in 6G, but more extreme. And there is some new ones. You see here this HCS, abbreviated human-centric devices. Well, this is interesting. The idea that 6G can give us more human sensory capabilities, being able to, the brain, talk to devices. As we've seen in some movies many years past, the brain talking to devices very fast, like almost human-grade sensory devices. And for this, 6G is positioned to be that. So if you look at the next chart over here, this other picture, classify as driving applications, driving trends, enabling technologies. From the wireless perspective, you see here more bits, more spectrum, more reliability. What's interesting here for this particular visionary slide, end of the smartphone era, is it really the case that with 6G, this may change from a smartphone to perhaps a goggle or glasses? Is that really the case? Well, we'll see. But the idea is human sensory devices. So definitely more spectrum beyond 5G millimeter wave FR2, more type of applications related to big data, machine learning, artificial intelligence, but more massive, extreme. Some of the key requirements, as you see, compared to 5G, 1 terabits per second, compared to 1 gigabits per second, 1 milliseconds, less than 1 milliseconds latency compared to 5, and more reliable type of networks. This particular slide talks about, similarly, use cases that are expected. In addition to human sensing type of grade, imaging, being able to be even more accurate, seeing inside vehicles, seeing in the dark with cameras that are very sensitive at terahertz type of frequency ranges. There is others that are being talked about as well. I'll let you take a look at the slides at some point in the future. So what are the key use cases that have been driving this type of trend? We've talked about video, but going forward, network machines, XR, virtual reality, augmented reality, human type of related, holographic imaging, security imaging, and in the data centers, why not? Terahertz, short range type of communications as well. So clearly, if you look at this quote from Ericsson, the advent of mobile extended reality technology, and here's the key, with complete human grade sensory feedback will require even higher data rates and capacity. And you see precise positioning and sensing. We're seeing UWB, micro positioning technologies will continue to be the case. Extremely low latency and end-to-end with edge cloud processing. So let's go back to 5G. So that's a little bit of what's coming up in the next 5-6 years. It's never too early to start getting ready for that. If you look at 4G to 5G transition, significant increase on ATE, test, total available market, TAM. On 5G was kind of simplistic if you look at it backward, if you look back. 4G, microcells, smartphones, has so many ICs, but going to 5G, we cross this wall right here in between, in which we have a 10x frequency and bandwidth multiplier. Opens the door for new devices. For example, on the 5G, you get this cut the cord, right? So instead of having optical and copper going to your hotspot in the home, why not go to a 5G, high-speed link, and you have this vertically pocket router, you have this Wi-Fi without having to install, this expensive cord via optical or copper. You have massive MIMO, you have small cells, and the complexity of the smartphone, as you can see between the green and the orange colors, the orange means a millimeter wave. All smartphones today in 5G here in the United States are millimeter wave capable. All of them, in terms of the main brands. So 5G I'm talking about. So clearly the complexity of the smartphone has increased to the point that the test intensity has increased. There's more carrier aggregation, more frequency bands. OTA testing is also a trend that we cannot ignore, that it will be more prevalent, likely so, as we go into 6G terahertz. So clearly a significant shift in terms of ATE TAM has caused between 4G and 5G. What are the frequency ranges that are expected for 6G? Around 3 terahertz, maybe 95 gigahertz to 3 terahertz in that range. But important here, I want to point out that we're getting close to nanometer. Nanometer, that's light That's photonics. And what's happening is that photonics is also a trend that we cannot ignore in regards to test. Whereas this presentation is about wireless tests or RF testing, 5G capacity, faster pipes are clogging the backhaul, are clogging the data centers, because you get all these wireless devices coming to the backhaul, to the data centers. So we have a bottleneck happening. And also that's an opportunity for innovation from the test point of view. Need to optimize the test cell, need to optimize the test time from minutes to seconds, need to be able to integrate the photonics and electronics instrumentations so they coexist in an efficient way. So yes, millimeter to terahertz, but also nanometers in the case of photonics ICs. So frequency. This slide is publicly available from the Qualcomm site. And I've been tracking this for the past 3 years. And yeah, you got this 95 gigahertz now shown. Is it going to be for 6G or 5G? Well, we'll see. But the trend is clearly to more frequency in the higher bands, more carrier aggregation, more phase antenna arrays, because the lambda, the wavelength is becoming so small that you can fit more and more and little antennas that are even smaller than the actual IC going into terahertz. So clearly, higher bandwidth, more frequency are the test challenges for ATE type of instrumentation. Now, why testing? If you look, here's a picture from the internet. Millimeter wave devices are now part of smartphones, at least 2 of them, perhaps more in the future. If just that one device fails, you have to return the entire smartphone. You know, it could be a $1,000 smartphone, a premium one. Clearly, don't want to have any of these transceiver devices fail. So therefore, clearly, testing to establish a quality brand is key. Be able to either functionally, reliable, quality type of testing that is very, very important. So one asks oneself, what are the type of tests that needs to be done? Well, quite frankly, the test list for this type of millimeter wave and terahertz really doesn't change that much, with perhaps the exception that the question of over-the-air testing becomes even more so interesting. I'm going to say interesting. It's not clear yet whether or not that will be the dominant test use case for millimeter wave or terahertz, but it becomes a trend that we have to watch. Therefore, this question here about OTA being forming, is that really the trend? Should we keep an eye on that? Well, we should, but the jury is still out for whether or not that trend will be the use case of the future. It is a trend, however, that cannot be ignored. But if you look at everything else in the test list, doesn't matter if it is a millimeter wave RFIC or the IF intermediate frequency, it's a similar type of test list: gain, filters, PLL, HLR, EVM, phase trimming, things like that. So the key question is really the interface to the IC from contacted to perhaps OTA as we go forward. So clearly, if OTA indeed is a trend, it is very important we as test engineers continue to ask ourselves the question, what type of OTA testing am I doing? Am I doing a far field? So if this is the dot, as you can see here in the white box, millimeter wave IC antenna array, and the D is the aperture, if you wish, of the millimeter wave device. Am I testing in the far field, near field, or reactive near field? That question needs to be answered because it has a direct impact on the physical size of the chamber that covers that dot device under test. It can be very, very small if you're on the reactive, or it could be large, more for R&D, DVT type of environments. So if it's very small, then we can be thinking about a handler for these packages. So this question is important and is being explored as well. And the other one is, what are my test insertions? Should I do silicon wafer test for millimeter wave, for terahertz? And if I do, what about the contacts? That's a challenge. How many sites can I test? 1 site? 2 sites? Today, sub 8 gigahertz, sub 6 gigahertz, you're on the 8, 16 type of sites testing. So for millimeter wave, can I do more than 2, 4? All depends too on how reliable that probing interface can be for the wafer. And then there is other options: module testing, functional testing, OTA, not OTA, sub-assembly, final product test. But the one message I want to say in this chart is with Teradyne, we got you covered. It doesn't matter if it's millimeter wave, wafer probe, or final product. We have products, millimeter wave test solutions in the UltraFlex millimeter wave test equipment, as well as with LightPoint in the IQ Gig 5G that cover the entire 5G millimeter wave FR2 range. So clearly, these are the questions and the challenges that are coming. I'll let you take a look at this chart. It tells you why certain insertions will be needed. It tells you what are the type of things or why we're trying to cover. But there is absolutely a trend towards making this type of insertion. Now, which will be the optimal test insertion process? As volumes increase, as vendors are getting their feet wet, so to speak, it will settle into a preferred method. We're still not there, but it's very close. We expect similar test strategies options for terahertz. It's just higher frequencies and higher bandwidth. So this one slide here is to convey the message. There is a large installed base of sub-6 gigahertz ATE equipment all over the world. For Teradyne, there's hundreds of them that have been used for the past many years. Therefore, as we go from 1G to the next G, we've got to have a strategy of upgrading the installed base. We have to have that. And with Teradyne, you do. In fact, an UltraWave MX44 millimeter wave tester is just a simple upgrade inside the tester head. There are no additional layers that need to be added on top of it, one layer after the other that requires calibration, type of complexity. It's all calibrated to the blind mate inside the tester head, residing next to the sub-6 gigahertz, sub-8 gigahertz type of testers. So therefore, customers can redeploy the existing installed base into millimeter wave very, very quickly without having to throw away the hundreds of existing testers for sub-6 gigahertz. This is clearly a value proposition from Teradyne UltraWave, MX44, and millimeter wave instruments. So, in summary, 5G is here. Since 2018, we've been tracking this initial ramp. And it's ramping faster than 4G. It has brought about 2 to 3 times an RX test multiplier in terms of time. Therefore, just like the wafer capacity, ATE capacity continues to be an important factor from the business perspective. 6G is only 4 to 5 years away, and it takes time to develop the standards. It takes time to develop test strategies. So it's ahead of us, not too far. And transceivers will require integrated microwave, sub-8 gigahertz, millimeter wave, FR2, and terahertz type of bands. Multi-band, multi-frequency, multi-spectrum, multi-bandwidth type of challenges. So we need to continue innovation on test techniques from millimeter wave to terahertz, contacted signal delivery, perhaps even OTA. And let's not forget, this trend is also putting stress in the backhaul and data centers in photonic ICs at the nanometer level. So clearly, we have seen a change in the past 4 years for 4G to 5G. New strategies are being developed, new test challenges. We continue to monitor those. And Teradyne is at the forefront of the 5G era and into 6G in the next 5 years. So as a summary, I thank you very much for listening to this presentation, and perhaps there are some questions I can answer next.
Thank you, George. Sorry, I have to unmute myself. We got a few questions, Q&A. First, George, I think the audience is interested to know that will multi-band microwave millimeter wave terahertz test instrument be likely required for 6G?
That has been the trend over the past 30 years. The old bands never go away. The analogy I have is like a TV monitor, right? If you look at the backside, you got the old, AV, you got HDMI, you got all of it. They don't go away because it has to be backward compatible. So the answer is yes. Future 6G transceivers will require multi-band, micro, milli, terahertz type of bands to be worldwide ready. Absolutely. Good question.
Thank you. The next question is, will most 6G device be smartphones, or there might be something else more predominantly used 6G technology?
Yeah, excellent question. The promise of 6G is human-centric type of sensory type of devices. The ability to put some sort of, virtual reality of some sort. It would change from this perhaps a big virtual reality goggles today, maybe something just in the ears, but being able, or it could be implanted. There is talks about implanting devices inside the brain for people who need it, for perhaps medical reasons. But yes, these are new devices that will come up that will increase the volume beyond just smartphones. On the other hand, I don't believe this will go away that quickly. I think these are here to stay for a long, long time. So I think there will be complementary devices to smartphones rather than total elimination of smartphones.
Great. Another question is, you mentioned the frequency range of the 6G. What do you expect the frequency range? If you can give a little bit more information.
Yeah, so last year, the FCC in the United States made an announcement that opened up 95 gigahertz spectrum, above 95. And when the release was made by the FCC, was in the context of paving the way to 6G. So the question is 95 gigahertz sort of like the low end of 6G, and maybe the upper end of 5G? There's conflicting information. I've seen 5G being talked about even 120 gigahertz, 114, 115 gigahertz. So, we'll see in the next few years what happens to the WRC, adopts the conventions of what is 5G, 6G, and when the 3GPP, as you said, adopts also those conventions. But 3 terahertz is thought to be about, the upper range for 6G.
I think we have time for one more question. How will bioethical considerations of AI affect the development and the rollout of associated ICs? Will this be a potential major roadblock?
So biological, you're talking about biological?
No, bioethical considerations.
Well, it's a good question. I'm not the expert on that particular subject. I have to admit, I don't think I can answer that question. It's beyond my skill level here. But good question. I'll take a look at that.
Okay.
Okay.
Thank you.
Well, actually, Hung-Jun, we have time to go into the other questions if you want.
Okay. Sounds good.
Are both UltraFlex and the J750EX going to have 5G and 6G millimeter wave capability?
So the current announcements from Teradyne are on the UltraFlex, which are primarily used for what we call flagship type of transceivers and connectivity devices. These are devices primarily targeting smartphones. So the current time, that is the focus, is to incorporate our millimeter wave solutions in the ultraflex type of tester. And we have the full spectrum millimeter wave and sub-8 gigahertz already released and announced. Yeah.
We have another question associated with the test cost, right? With more tests required, the actual device cost will be higher. So what will be the most critical barrier?
Yeah, so that's a good question, right? How much of a functional test needs to happen at silicon wafer level versus module level versus system test? That's the one chart I show, it shows all the possible insertions. And some of those would be optional. Some would be like, you got to do it. And some of those we don't know. But the key has to be with how much functional test. So will it be more built-in self-testing being put into devices like it's been the trend over many years at millimeter wave in this case? So that is a key question. So excellent point. And the other question is characterization. Even if certain tests are not done in production, what if you have a failure? What if you have a field return? You still need to go back to the AT tester and test it at functional level, at speed, so to speak, at the millimeter wave frequency. So people need to have both, in other words, strategies. And over time, some tests may be reduced, as is the case always. It's been the case in sub-8 gigahertz until the optimal test list is developed. Yes.
Great. Thank you again, George.
To once again thank our sponsors who've made this event possible and made it available without registration charge to the attendees. Our premier sponsor, Cohu, our emeritus sponsor, JonsTech, our honored sponsors, ISC, iWin, and TSE. Our distinguished sponsors, Backer Hotwatt, Innovative Circuit Engineering, JMT, Nidec SVTCL, R&D Altanova, UI Green. And lastly, our exhibitor sponsors, ELES, MJC, Phoenix Test Arrays, and Smith's Interconnect. So I'd like to thank all of them, and also give an extra special shout out to Cohu, who is our premier sponsor, and they are the market leader in test interface solutions for very challenging applications in different areas. And also would like to thank ISC, who's the global #1 total test solution provider with products in the elastomer socket and interposers, spring pin socket solutions, and burn-in socket solutions. So once again, I thank all the sponsors. I thank you as the attendees. We look forward to seeing you again tomorrow at 7 a.m. Pacific time. I wish everybody a great day, so thank you.